Good day dear students. In this video we shall see about the module 3 beam elements. We shall see how the derivation for the Hermite shape function for the beam element has been done, and also certain points or formulas to be remembered while solving the problems. So this will basically deal on the derivation of the Hermite shape function for the beam element. So in this slide you can clearly see a beam element that has been drawn. So it has two nodes, 1 and 2. So at node 1 you have theta 1 or the slope del v by del x, and at node 2 you have the second slope del mu by del x theta 2. So there are two nodes and theta 1 at node 1, theta 2 at node 2. So the figure shows a beam element having two nodes. At each node there are 2 degrees of freedom. So the field variable mu of x in terms of shape function is given by the equation mu is equal to h into q, where h is the Hermite shape function represented by h is equal to h1, le by 2 into h2, h3, le by 2 into h4, and q is nothing but the nodal displacement vector. So it consists of mu1 theta 2 and mu3 theta 4. So theta 1 mu1 and theta 2 represent the node 1, and mu3 and theta 4 represent the node 2. So in order to find h1 we will try to derive the value for the variables h1, h2, h3 and h4 in the coming exercise. So to find the value of h1, since there are 4 degrees of freedom, we have to assume a polynomial displacement model has h1 is equal to a0 plus a1 zeta plus a1 zeta square plus a2 zeta cube. So a0, a1, a2 and a3 are the generalized coordinates that are required to be determined from the nodal conditions. So at node 1 h1 is equal to 1, neta is equal to minus 1, and we can rewrite the equation as 1 is equal to a0 plus a1 a0 minus a1 plus a2 minus a3. So let this be equation number A. Similarly at node 1 del differential of h1 by del neta is equal to 0 and neta is equal to minus 1. So we can write del h1 by del neta is equal to a1 plus 2a2 neta plus 3a3 neta square. So substituting the value of neta as minus 1 in this equation, we get 0 is equal to a1 minus 2a2 plus 3a3. So let this be equation B. Similarly at node 2 h1 is 0 and neta is 1. So I can rewrite the equation as 0 is equal to a0 plus a1 plus a2 plus a3. Now at node 2 the differential of h1, that is del h1 by del neta, is equal to 0 and neta is equal to 1. So I can rewrite this as 0 is equal to a1 plus 2a2 plus 3a3. So the adding equation A and C, we get 1 is equal to 2a0 plus 2a2. So let this be equation number E. Now when we add equation B and D, addition of equation B and D we shall see in the next slide. So adding equation B and D, we get 0 is equal to 2a1 plus 6a3. So let this be equation F. So a1, from this we can deduce a1 is equal to minus 3a3, and from equation C we can rewrite it as 0 is equal to a0 plus a1 plus a2 plus a3. So a1 is nothing but minus a3. So substituting this in this equation, we get 0 is equal to a0 minus 3a3 plus a2 plus a3. So 0 is equal to a0 plus a2 minus 2a3. So a0 plus a2 is equal to half. Thus equation G becomes 0 is equal to half minus 2a3, hence a3 is equal to 1 by 4. Similarly, a1 we can reduce as minus 3 by 4, a2 has 0 and a0 has 1 by 2. Now we have found out the values for a0, a1, a2, a3. Now substituting this in the equation 4.57, in the equation 1 we get h1 is equal to a0 plus a1 neta plus a2 neta square plus a3 neta cube is nothing but half minus 3 by 4 neta plus 0 plus 1 by 4 neta cube. Thus h1 or Hermite shape function 1 is equal to 1 by 4 into 2 minus 3 neta plus neta cube. So this is equation number 2, wherein we have found the value for h1. Now similar to how we have found h1, the next exercise will be to find the value of h2. So again let us assume a polynomial differential model for h2, where h2 is equal to a0 plus a1 neta plus a2 neta square plus a3 neta cube. So a0, a1, a2 and a3 are the generalized coordinates that are required to be determined from the nodal coordinates. So at node 1, h2 is 0, neta is minus 1. Hence we will write it as 0 is equal to a0 minus a1 plus a2 minus a3. At node 1, the differential of h2, so del h2 by del neta is equal to 1 and neta is minus 1. But del h2 by del neta is nothing but equal to a1 plus 2a2 neta plus 3a3 neta square. That is, differentiating the equation h2 with respect to neta, we get this equation. So we can write it as 1 is equal to a1 minus 2a2 plus 3a3. Similarly, at node 2, h2 is equal to 0 and neta is equal to 1. Hence the equation 3 becomes 0 is equal to a0 plus a1 plus a2 plus a3. And at node 2, del h2 by del neta is 0 when neta is equal to 1. Hence the differential equation will be rewritten as 0 is equal to a1 plus a2, a1 plus 2, a2 plus 3a3. Now adding equation A and equation C, we get 0 is equal to a0 plus a2, and adding equation B and D, we get 1 is equal to 2a1 plus 2 plus 6a3. But from equation F, we know that a1 plus 3a3 is equal to half, or in simple words, a1 is equal to half minus 3a3, and 0 plus a2 is equal to a0 plus a2 is equal to 0. Now substituting this in equation C, we get a1 plus a3 is equal to 0, but a1 is equal to half of minus 3a3. Hence I can write half minus 3a3 plus a3 is equal to 0, or a3 is equal to 1 by 4. So after finding the values of a0, a1, a2 and a3, substituting this in equation 3, so equation 3 can be rewritten as h2 is equal to a0 plus a1 neta plus a2 neta square plus a3 neta cube, that is equal to 1 by 4 minus 1 by 4 neta minus 1 by 4 neta square plus 1 by 4 neta cube, or in simple words, h2 is equal to 1 by 4 into, taking 1 by 4 outside, 1 minus neta square plus neta cube. So this becomes equation 4, wherein we have found out the equation for the Hermite shape function h2. Similarly, next we have to calculate, or we have to find out the shape function for h3. So we will repeat this exercise once again, wherein we will calculate the shape function h3. So to find out the Hermite shape function h3, let us assume a polynomial displacement model wherein h3 is equal to a0 plus a1 neta plus A2 neta square plus A3 neta cube. So let this be equation number 5. Now A0, A1, A2 and A3 are the generalized coordinates and are required to be determined from the nodal conditions. So at node 1 H3 is 0 and neta is minus 1. So I can rewrite the equation number 5 as 0 is equal to A0 minus A1 plus A2 minus A3. Similarly, differential of H3 at node 1 is 0 and differential where neta remains same, zeta is minus 1. Hence del H3 by del zeta is equal to 0, zeta is equal to minus 1. But del H3 by del zeta is nothing but the differential of equation number 5, which can be written as A1 plus 2A2 zeta plus 3A3 zeta square. Now substituting the values in this equation, we can rewrite this as 0 is equal to A1 minus 2A2 plus 3A3. So at node 2 H3 is equal to 1, zeta is equal to 1. Hence the polynomial function can be written as 1 is equal to A0 plus A1 plus A2 plus A3, and differential at node 2, that is del H3 by del neta is equal to 0 and neta is equal to 1. So the equation becomes 0 is equal to A1 plus 2A2 plus 3A3. So let these equations respectively be A, B, C and D as mentioned in the slide. So now adding equation A and C, we get A0 minus A1 plus A2 minus A3 is equal to 0 plus A0 plus A1 plus A2 plus A3 is equal to 1. So removing the common terms and adding, we get 2A0 plus 2A2 is equal to 1. Similarly adding equation B and D, that is A1 minus 2A2 plus 3A3 is equal to 0 and A1 plus 2A2 plus 3A3 is equal to 0, we get 2A1 plus 6A3 is equal to 0. So equation E is deduced now, that is A0 plus A2 is equal to half and A1 plus 3A3 is equal to 0. So from C we have A0 plus A1 plus 2A2 plus A2 plus A3 is equal to 1, or half plus A1 plus A3 is equal to 1, or half minus 3A3 plus A3 is equal to 1, because A1 is nothing but minus 3A3. So the value of A1 A3 is deduced as 1 minus 1 by 4. So substituting this and finding the values for A0, A1 and A2, we get A1 has 3 by 4, A0 has half, A2 has 0. Now substituting these values in equation 5, we get the Hermite shape function H3. So the function H3 can be written as A0 plus A1 neta plus A2 neta square plus A3 neta cube, that is equal to half plus 3 by 4 neta zeta minus 1 by 4 zeta cube. So this will be equation 6. So here I will be taking 1 by 4 common, and inside I will be keeping 2 plus 3 zeta minus zeta cube. Next step is to find the last function H4. So again let me assume a polynomial displacement model for H4, that is equal to A0 plus A1 zeta plus A2 zeta square plus A3 zeta cube. So this is equation number 7. Now A0, A1, A2 and A3 are the generalized coordinates and these are required to be determined from the nodal conditions. So at node 1 H4 is 0, zeta is minus 1. So the equation can be rewritten as 0 is equal to A0 minus A1 plus A2 minus A3. So differential of H4, that is del H4 by del zeta is equal to 0, and when zeta is minus 1 at node 1. So the differential of the equation H4, that is del H4 by del zeta is equal to A1 plus 2 A2 zeta plus 3 A3 zeta square. So let this be equation B, which will be rewritten as 0 is equal to A1 minus 2 A2 plus 3 A3. Now rewriting at node 2 we have h4 is equal to 0, zeta is equal to 1, hence 0 is equal to a0 plus a1 plus a2 plus a3, which is equation C. Del h4 by del zeta is equal to 1, zeta is equal to 1, hence we will write it as 1 is equal to a1 plus 2a2 plus 3a3, which is equation D. So adding equation A and C we get a0 minus a1 plus a2 minus a3 is equal to 0, a0 plus a1 plus a2 plus a3 is equal to 0, we get has 2a0 plus 2a2 is equal to 0. Adding equation B and D we get a1 minus 2a2 plus 3a3 is equal to 0, a1 plus 2a2 plus 3a3 is equal to 1, we get it has 2a1 plus 6a3 is equal to 1. So further simplifying, a0 plus a2 is equal to 0 and a1 plus 3a3 is equal to half. From equation number C we know that a0 plus a1 plus a2 plus a3 is equal to 0. Since a0 plus a2 is equal to 0, we can remove those two terms, and a1 plus a3 is also equal to 0, we can remove those terms. So but a1 is equal to half minus 3a3. So we can rewrite this as half minus 3a3 plus a3 is equal to 0, or a3 is equal to 1 by 4. So we have found one variable, that is a3, which is equal to 1 by 4. So similarly, substituting 1 by 4 in equation F, we get the value for a1. So the value for a1 is calculated to be minus 1 by 4, and similarly substituting the values in other equations, we get a0 as minus 1 by 4 and a2 has plus 1 by 4. So substituting the values of a0, a1, a2, a3 in equation 7, we get h4 is equal to a0 plus a1 zeta plus a2 zeta square plus a3 zeta cube, that is equal to minus 1 by 4 minus 1 by 4 zeta plus 1 by 4 zeta square plus 1 by 4 zeta cube. So h4 is equal to, taking 1 by 4 term common outside, minus 1 minus zeta plus zeta square plus zeta cube. Now the Hermite shape function is nothing but h is equal to h1 le by 2 h2 h3 le by 2 h4. Now the terms for h1 h2 h3 and h4 we have calculated, and we have written down as equation in the previous slides. So now we are combining it to write the Hermite shape function. So the Hermite shape function is nothing but h is equal to 1 by 4 into 2 minus 3 zeta plus zeta cube, le by 8 into 1 minus zeta square plus zeta cube, 1 by 4 into 2 plus 3 zeta minus zeta cube, le by 8 into minus 1 minus zeta plus zeta square plus zeta cube. So this is equation 9. Let this be equation 9. This is the Hermite shape function for the beam element. So if a question arises, to derive the Hermite shape function, you have to write the shape function from the beginning and derive all the variables and write down this matrix. So this is the end of the derivation of the Hermite shape function for a beam element. So in the next slide we shall see the various shapes. Here you can see derivation of a Hermite shape function for a beam element. So the variation of the shape function is shown in this figure. For h1, h2, h3 and h4, we have the values of v1 has 1 and theta 1 has 0 for h1 at node 1, and at node 2 we have mu 2 has 0 and theta 2 has 0. Similarly, for h3, h4, h2, h3, h4 also we have the shape functions. So this is the variation of the shape function. Okay, this is the formulation for the nodal forces and the bending moment. So this is similar to what you have studied in your lower semesters. Uh, you are expected to remember this formulation so that it will be easier for you to recall while solving the problems. So left hand side shows the loading case. A beam, it is fixed at both the ends and a point load is acting exactly at the center. So at node 1 the force is represented as P by 2 and bending moment is represented as PL by 8, and at node 2 the load is represented as P by 2 and the bending moment is represented as minus PL by 8. If it is a uniform load UDL, uniformly distributed load, P naught, has shown in the second row. So if P naught is a uniformly distributed load, then at node 1 the force will be P naught into L divided by 2 and the bending moment will be P naught L square divided by 12. For node 2 it will be again P naught L divided by 2 and the bending moment will be minus PL square by 12. Suppose it is a uniformly varying load. In that case it will be a uniformly varying load, that is maximum from node 1 to 0 at node 2. Then in that case it will be 7 P naught L by 20 and P naught L square divided by 20. For node 1 it will be the bending moment, and the load at node 2 will be 7 P naught L divided by 20 and bending moment will be minus P naught L square divided by 20. Suppose it is a triangular load as shown in the figure, then at node 1 the load will be P naught L divided by 4 and bending moment at node 1 will be 5 P naught L square divided by 96. At node 2 the load will be P naught L divided by 4 and the bending moment will be minus P naught L square divided by 96. So with this we have covered all the derivations for the beam element. In the next videos we shall see the solution for some of the simple problems.